I am Amandeep 19 ME 30062. We have done a group project of dynamics of machine, subject code ME 30062.
My name is Sudhanwa Karni. My roll number is 19ME10098.
Hello, sir. My name is Mulayam Yadav. My roll number is 19ME10039. So our group has chosen this first question. We have chosen this question as it interests us the most since we study IC engine in mechanics section and in our ATF course. Now I would like Sudhanwa to proceed with the simulation part.
Thank you, Mulayam. So, sir, we have modeled this IC engine mechanism where this is piston skirt, piston dome, uh, piston rings. Some of these are pressure rings, and last one is oil ring. This is piston pin. This is connecting rod. This is crankshaft, flywheel, and this is where the motor lies. So let me show you the simulation of how it will work when we apply it a constant angular velocity. Okay, sir, so that was how it worked. So analyzing ground forces. So let me show you the plots of the ground forces. Sir, here there are various options out of which we will be choosing forces. Next, reaction force, and then magnitude. And as we tick this tick, we will get this nice graph with constant angular velocity. And if we want to see the reaction moment, same, the procedure is again same. Forces, reaction moment, magnitude, and let me select the mate and then unselect all these. Okay. So as you can see, this is the reaction plot of the reaction moment versus the time. We have made these parts in SolidWorks itself and then assembled them all, and all these parts are dimensions of all these parts are taken from internet. Reference is Google, and the dimensions are selected such that they are in synchrony with practical dimensions of whatever the engine is used in cars. So I would like Amandeep to proceed further.
Thank you, Sudhanwa. First of all, I would like Sudhanwa to go to the coding part.
Okay.
Actually, in this system, what we have assumed is that for the analysis of this IC engine, we have assumed that this mechanical system works in 3R1P chain. In this 3R1P chain, we have assumed that there is constant offset present in it, and we have also assumed the concept of mass apportionment. Here, for the analysis, we started with the analytical mechanical approach, in we have taken the generalized coordinate, that is theta, and the crankshaft distance that it will travel from its top dead center to its bottom dead center, that is SD. In this, after we have after writing the generalized coordinates at a generalized position, we have written the Lagrangian part of it, in which we have also assumed some constraint on the mechanism through which it will work. Since we have assumed the model analysis through the matrix method, we have created different matrices. And in these matrices, we have taken either the generalized coordinates or their derivatives or their double derivatives. For finding out the derivatives and double derivatives in the matrix itself, we have defined some functions which are shown in the slide. After this, I would like to say that we have created our equation. That equation is the equation of motion which the slider will follow along with the theta, which will be time dependent. These time dependent quantities are shown here, and equating them to zero will show us the equation part. After this, we would like to go down, in which we have taken something that is what we have assumed is that instead of taking this as a single mass element, we have assumed it to be a spring providing two force member in the coupler part. After this, I would like to go down. Since it is not very easy to solve these equations, what we have assumed is we have followed the principle of Hamilton's. What the principle of Hamilton says is that instead of taking the number of equations equal to the generalized coordinate, we have taken equations equal to the 2 times the number of generalized coordinates by assuming that Hamilton's principle is followed, which are taken as Z11, Z12, Z21, Z22, which are shown down. After taking this, what we have assumed is that we have written the LHS and RHS part of the equation, and then we have tried to solve them through our solver, that is ODE int. In this ODE int, we have assumed some initial conditions, and those initial conditions, along with the numerical analysis part, we have shown two graphs. In this graph, you can see that this is the variation of angular, that is theta, and the slider distance along with time. As we can see that we can see a triangular curve because the slider will slide the distance between its top dead center and its bottom dead center. Along with this, we have also shown in the graph the velocity, the angular velocity and the position, along with the velocity and position of the slider. As we can see that they are changing direction throughout in position where we have top dead center and the bottom dead center. After this only mechanical analysis, we would like to find out what are the ground forces that are working. For the ground forces, what we have assumed is that we have apportioned the mass of the coupler on two parts. One is on the slider and one is on the end of the uh, rocker that is moving all through the 360-degree angle. I would like Sudhanwa to proceed with the slides, to go to the slides to explain that part.
Thank you, Amandeep.
In this slide, what we have assumed is that we have apportioned the mass and such that the center of mass lies at the real center of mass of the coupler, but we have distributed its mass to its end so that we can get two equations, actually three equations. One is in the x direction, second is in the y direction, and third is the moment about the position O, through where the coupler is rotating about 360 degrees. Now I would like Sudhanwa to proceed from the next slide.
Yeah, so in the next slide, as Amandeep told in the previous slide, that we have three equations, two of forces, one in x direction, one in y direction, and the moment equation. So this is the equation of force in the x direction, left hand side of the force equation. So here, as we can see, the first term m2 rho 2 plus ma r plus capital M into r this term we have to minimize, and we can choose the ρ2 value by connecting the big ball at the other end of apportioned mass ma of the connecting link, such that the ρ2 will be negative, and so that we can minimize the fx and fy. So one thing we can do, that we can select ρ2 such that we can totally nullify fy, but there will be considerable amount of fx due to this capital mass M, which is the total reciprocating mass, mb, that is another side of apportioned mass of connecting link, and the mass of piston. So we have to choose ρ2 in such a way that the total magnitude of fx and fy is minimized, which can be done by selecting the appropriate value of zeta between 0 and 1, approximately 0.5, such that the both value of fx and fy will be approximately same, and so that the total magnitude of ground forces will be minimum. So we have neglected the second order terms here, and now let me show you what we have done in coding part. We have also tried to code the same phenomenon in SymPy. So here are the declared variables, and this is theta 5 lambda, which is r by l, and this is the general equations which was discussed in the class, and we have assumed some practical values of the masses and lengths of the link according to the BMW engine. And so these are the same equation as we have seen in the slides itself, and plotting them we have got these graphs. This is graph of fy, and this is the graph of fx, and this is the net graph of reaction magnitude, net reaction magnitude of net reaction force. So yeah, that's it.
Okay, so thank you, Sudhanwa and Amandeep. With this, we'll conclude our project. Hope you would like it. It was really good experience to study dynamics of machines under you. Thank you so much, sir.